Welcome, everyone. It's my pleasure to introduce Jonathan Luke today. So he did his PhD in Princeton in 2012 with Igor Rodnyansky. And then he was an NSF postdoc at the University of Pennsylvania. Next, he was in MIT as well as Cambridge. And since 2016, he's in Stanford, and currently he has a position of associate professor there. And today we're going to hear a talk about singularities in general relativity. So please, Jonathan, the floor is yours.
Good afternoon. Today I'm going to talk about singularities in general relativity. Of course, already in popular science, we know that general relativity predicts the existence of singularities, often associated with black holes or the Big Bang. Today, I'd like to talk about the mathematical story of singularities. In particular, I want to show how general relativity motivates very interesting questions in mathematics, in particular in differential geometry and in partial differential equations. And on the other hand, how mathematics is used to understand singularities in general relativity. So let me start from the very beginning with a very, very quick introduction to general relativity. So for a mathematician, perhaps the easy way to think about general relativity is the following. There are two main things here. First, the main object of study of general relativity would be a Lorentzian manifold. So that is to say, we would have a spacetime, which is a 3 + 1 dimensional manifold. 3 + 1 meaning that we have 3 space and 1 time dimension. So I'll denote this by M. And this has a Lorentzian metric G. So like a Riemannian metric, it's a symmetric bilinear form on the tangent space. However, it has signature minus plus plus plus, so the eigenvalues have signs minus plus plus and plus, unlike the Riemannian case where the metric is positive definite. So the basic example of a Lorentzian metric is a Minkowski spacetime. This is the spacetime of, in fact, special relativity. The manifold here would be R4. I write it as R3 + 1 to emphasize that there are 3 space and 1 time dimension, and I denote the metric by M for Minkowski. And this is just the diagonal metric with -1 + 1 + 1 + 1, obviously satisfying the sign condition. So already you can see in Minkowski, but more generally for any Lorentzian metric, that once you have this metric, you can think about causality. So that is to say, you can think about vectors, right, where you look at Gxx and you want to understand what the sign of it is. Because it's now not positive definite, there's a 0 set, and it takes the form of a cone. Okay, and this is a vector, so that Gxx is 0. And you should think physically, this is the direction where light travels. And you and I, who travel strictly less than the speed of light, would travel in directions which are like this. And these are called time-like directions. And if I have a direction which is outside the cone, for which Gxx is positive, this is called spacelike directions. Okay, so this is the first ingredient for the theory of general relativity. But we are not just interested in just all Lorentzian metric. We'll be interested in Lorentzian metrics which satisfy a PDE. And this is the celebrated Einstein's equation written down by Einstein a little bit more than 100 years ago in this paper. And this is the equation, and we would like to consider only metrics which satisfy this equation, which is supposed to describe gravitation. So what's this equation? Well, the equation has 2 sides. Well, the left-hand side depends only on the geometry of G. So look at the Lorentzian metric. The first term is the Ricci curvature, but the second term is -1/2 of the metric itself multiplied by the scalar curvature. Now, the right-hand side depends on the matter content of the space-time through this tensor T, known as the stress energy momentum tensor. So the way that this is a theory for gravitation is as follows. So once you know the matter field, right? The equation tells you how curvature looks like. So this, in some sense, determines the geometry. And for freely falling observers, observers which are just attracted by the gravitational force, would live in the space-time and just follow the time-like or null geodesics in the space-time. Now, unlike Newtonian gravity, in fact, if you look at the Einstein's equation and look at the special case where there's no matter at all, set T here to be 0, right? This is the vacuum case. The Einstein's equation is still highly non-trivial. In this case, the equation reduces to just Ricci equals to 0. And it turns out that this is already very interesting. This is, of course, in stark contrast to Newtonian gravity, where if you have no matter, gravity is completely uninteresting. Here in Einstein's theory, you actually would still have gravitational waves, making it interesting. Now, for most of the talk, I'll be thinking about this equation. And it took a while to understand this historically, but now we understand that one should really think of this as a system of quasi-linear wave equations. So if you write it in an appropriate coordinate system, then you see that this is a wave equation, and you can ask questions that you ask for wave equations. So think of the original wave equation of D'Alembert, talking about a string, right? So what the equation can tell you is that if you tell me initially what the string looks like, its position, and how it's moving, its initial velocity, then the wave equation would tell you how the string evolves for all time. Okay? Now, similarly, you can ask this question for the Einstein's vacuum equation. Suppose I give you initial data appropriately formulated. I want to say that there is a solution that's determined by the data and the Einstein's equation. And this is, in fact, a starting point of the discussion of general relativity. It's the fundamental theorem by Schoelkieper and Gersch. So let me talk about it briefly. So the theorem says the following, exactly as I said, you want to have initial data. So I want to start with something I think of as, let's say, now. And this is a three-dimensional submanifold in the four-dimensional spacetime that I'm interested in. So this is sigma, and on which I want to give my initial position and velocity. Now the initial position would be the metric that's on this sigma, and I want to think about now as sort of fixing time. So this should be a space-like type of surface. So I want my g hat to be a Riemannian metric, that is to say it has to be positive definite. And I want to talk about how this sigma is moving inside M. In other words, how it's embedded into the larger manifold. So I would give what I wanted to be the second fundamental form, k hat. Okay. It turns out that one cannot arbitrarily prescribe g hat and k hat so that the Einstein's equation is satisfied. One has to impose some constraints. Let me not get into that, but just tell you that if you give me this initial data set with sigma g hat, k hat satisfying constraint equations, then the theorem of Schoelkieper-Gersch tells you that you can solve. There is a solution. Right, so this is the space-time, 3 plus 1 dimensional, so that in this space-time, Ricci is 0. You satisfy the Einstein's equations, and sigma embeds into this space-time with induced metric g hat in the second fundamental form k hat. Moreover, in fact, one can look at all the developments which are determined by the data. Okay, called these Cauchy developments. Among this class of Cauchy development, there's a unique up to isometry one, which is maximal. Okay, so there's the largest one. Every other development which is determined by the data must embed isometrically into it. Okay? So this theorem, as I stated it, only concerns the vacuum, but in the case where you have some appropriate physical matter fields, one can also have an analogous theorem as long as you put also appropriate evolution equations for the matter field. What's important about this theorem is, well, first, it constructs a lot of solutions, of course, to the Einstein's equation. But moreover, what's important is that this gives a dynamical formulation of general relativity. You start with data, and then you have a solution. And you can ask questions that you ask for dynamical problems, for evolutionary PDEs. For instance, you can say, well, suppose I give you initial data. Do I know that the solution is global? For instance, you can ask that suppose I give you a specific solution to the Einstein's equation arising from some data. I can ask the question of stability of the solution in the sense of if I perturb the data a little bit, will the solution stay close to the given solution for all time? You can also ask questions about genericity. What does the generic spacetime look like? In the sense that I would look at generic initial data, and I want to understand the spacetime arising from these data. And it will be from this dynamical point of view that I would like to understand singularities. So let's start with some examples so that we know, have some examples of singularities and know what to think about. So let's go back to our very basic example that we have already encountered, which is the Minkowski metric. I told you that this is the simplest example for Lorentzian geometry, but you can easily check that, of course, this metric being a constant coefficient metric would have zero curvature and therefore has zero Ricci curvature and therefore solves the Einstein's vacuum equation. Okay. So this is also a solution to the Einstein's vacuum equation. And in fact, because of that, we can think of it from the point of view of the Schoke-Brouwer-Gersch theorem. So let's draw this, right? So this is my T, this is my R3, right? So that's my Minkowski spacetime. So I can look at initial data. For instance, I look at the slice T equals 0. Okay, so that's my initial slice, has topology R3. And I would have initial metric, which is just the Euclidean metric given here, just the flat metric, and with 0 second fundamental form. And if you give me this data and you look at the maximal Cauchy development guaranteed to exist by the Schoke-Brouwer-Gersch theorem, you get exactly the Minkowski spacetime that's here. Okay. Now you can try to understand this solution, right? For instance, as I just said, you can try to ask, if I give you data, you look at the solution, is the solution global? Now you can ask this geometrically by asking, well, whether the solution is geodesically complete. And it's easy to check in the case of Minkowski that the solution is indeed geodesically complete. And indeed, the geodesics are just straight lines and they go forever in their affine parameter. Okay. Now, moreover, Minkowski is actually inextendable with the Z0 metric. So you cannot embed it into any bigger Lorentzian manifolds for which the metric is continuous. Well, remember the Schoke-Brouwer-Gersch theorem already tells you that, well, because Minkowski is the maximal Cauchy development of the data, it's the largest that's determined by data. But now this says it's more, well, it's really the largest. You can't extend it the period. You can't do anything larger with continuous metric. Now, I have this special solution. Again, as I just said, I can ask dynamical question about it after I know some qualitative features of it. Now, the question would be if I perturb Minkowski data a little bit, like perturb the data here, I would now want to look at the maximal Cauchy development of the perturbed data. I want to ask what's going to happen. And in fact, it's shown in a monumental work of Christodoulou-Kleinemann in 1993 that the Minkowski spacetime is globally nonlinearly stable. That is to say, the solution arising from perturbed data, they are in fact still geodesically complete. Well, in fact, if you choose appropriate coordinate system, you have asymptotic completeness. Everything converges back to Minkowski. Okay. However, not all spacetime has the property of geodesic completeness. Right? There is a large class which contains the perturbation of Minkowski. However, in general, if one look at general data, one must see geodesic incompleteness, and this is connected with singularities, which we want to think about in this talk. So the easiest way to see this is the Schwarzschild spacetime. Already was discovered in 1915, very, very soon after Einstein wrote down his equations. Although to understand the precise nature of the singularity took the community a while. So let me quickly say what the Schwarzschild spacetime is. Well, the manifold is R2 cross S2. In fact, everything is strictly symmetric. So this S2, everything's independent of this S2. The metric, let me call it G Schwarzschild for the moment. And you can write it down explicitly in local coordinate as follows, where M is a parameter and I'll consider all m positive. Okay. And perhaps the explicit form of the metric is not so important for this talk. What's important for now, for this talk, two things. First, this is a solution to the Einstein's equation. Okay, so this solves the Einstein's vacuum equation. And secondly, that in contrast to Minkowski, this has a singularity. Okay, so first of all, it's geodesically incomplete. So if you look at the geodesics, unlike in the Minkowski case, where there are some geodesics which will get to the end of the maximal Cauchy development in the finite affine time. But moreover, there's something even worse than just saying incomplete. There's something that is blowing up, which is associated with this incompleteness. And you can think of this as some singularity, for instance, in like how you would think about for PDEs. One way to say this is that curvature has a singularity. Okay, so if you look at this particular combination of curvature, which is curvature contracted with the self, which is independent of coordinates, it will go to infinity as you go to an r equals 0 boundary of the spacetime, which I'll say more about in a picture in the next slide. So this tells you that something actually grows to infinity. In particular, you cannot extend with a C2 metric because of the curvature blow up. However, in the Schwarzschild case, actually, one can say that something even worse is happening. That is to say, associated with the geodesic incompleteness, if you look at an observer following the geodesic going to the singularity, following this incomplete geodesic, as you go toward the singular boundary, in fact, the observer would be infinitely torn apart. Right? This is the infinite tidal deformation. And this is related, though not equivalent, to the statement that if you look at this solution, in fact, there's no extension with the continuous metric. Okay? And this is established by Spacelike quite recently. So here's the picture of Schwarzschild. So let me try to explain what this picture is trying to say. So as I told you, Schwarzschild is strictly symmetric. So let's forget about the dependence on the S2 and just draw a two-dimensional diagram, which is this. Well, this also has a conformal compactification, so that I take an infinite spacetime and put it on the slide. And well, the good thing about things being conformal is that I don't change the causal structure. So what you see as 45 degrees line here will still be null in the original spacetime. So what is this? What is this spacetime? So first of all, I want to think about it from the point of view of the theorem of Schwarzschild and Garish. I want to think about it as development of data. So data is this sigma. This is a three-dimensional manifold. Remembering that every point is a two-sphere. This has topology R cross S2. Okay. I've only drawn for you the maximal future development. The past would be similar. And now what you see is that there are two circles here. Well, this is saying that as you go to each end, things are actually asymptotically flat. Everything becomes like Minkowski here. Okay, so the data is such that everything becomes like Minkowski, and locally things are also like Minkowski here. Okay. However, as you develop the data, right, the data in this region is far from Minkowski. There's something very different that's happening. So the first thing is the following. So let's think of this script I plus here and here as, well, this is not part of space-time, but you can think of it as an idealized boundary, so that if you look at light signals, right, which goes like 45 degrees line, this is the endpoint of these light signals. So this is where faraway observers live to observe signal. This is known as fusion down infinity. Now you notice that in this space-time, there's a region which is a little bit more darker shaded, this region, for which if you are here and try to send signals, remember signals cannot travel faster than the speed of light, so it has to be within here, you can never reach far away observers. Okay, so this region is in fact a black hole for which you can't send signals too far away. Associated with this black hole, in fact, the boundary of this black hole, again, is not exactly part of the space-time, is a singularity. Right? So let's again say the words I said on the previous slide. So in what sense is this a singularity? First of all, it's incomplete. So if I look at the geodesic, gamma going here towards this boundary, this is incomplete. Okay. Now, if I go along this gamma towards here, in fact, I see that curvature blows up. In fact, also an observer going along here would be torn infinitely apart. Okay, so this is an example. In fact, the maybe most well-known example of a singularity that sits inside a black hole. Now, I want to understand in general what singularities look like. Well, the first question is, are there any other singularities, right? I have a PDE, I want to look at the initial value problem. I want to ask what are there other data which give rise to singularities? What do the singularities look like? So this type of questions was, of course, asked already very, very early on in the physics community, in a very well-known work of Lifshitz-Knotlikov in 1963. They want to ask the question whether generic solutions have singularities. Well, in fact, okay, you may even ask, are there even other singularities that you can construct? Right? Because the Einstein's equation is a very nonlinear, complicated PDE. There are not so many solutions you can write down explicitly. You want to ask whether you can construct a lot of solutions. So they consider things which look a little bit like Schwarzschild, but not exactly Schwarzschild, and take locally of the following form, where you should think that these A's are things which are finite, right? T equals 0 is a singular space-like hypersurface. These P's are constants which could, constants independent of T, but depending on X, which could be positive or negative, so that you have some singularities as T goes to 0. Well, they analyze this type of metric and use the equations and see what this implies. What they notice is that, well, there are fewer functional degree of freedom in this type of metric than in the initial value problem, right? So fewer than what one can impose. So in particular, what they say is, well, then these kind of singularities must be non-generic because, well, there are much more data than possible singularities of this form. Okay? So their argument is that, well, because of this, singularities is a very, very rare occurrence. You have Schwarzschild, of course, but that's very special. More recently, Ringström, in fact, give a proof that all convergent singularities with an appropriate sense must actually locally be of this form. Okay, so in fact, you can think if you want convergent singularities, this is everything that that one can write down. So what do we know mathematically? Well, mathematically, in fact, we know that in a joint work with von Davlos, that one can almost up to endpoint construct all solutions of the form that's given in the previous slide. Okay, so if you give me any leading order behavior, like in the previous slide, you can actually construct a singular solution to the Einstein's vacuum equation with the prescribed leading order behavior. Okay. So this constructs this large class of singularities. So in particular, there are a lot of singularity, but not that much. Still, this is highly non-generic. Right? The construction, in fact, has to be very carefully chosen. One has to start the construction at the singular hypersurface in order to avoid all the non-generic thing that one might potentially see. Okay. Now, this is consistent with the fact that stability is not expected, and stability is only known mathematically if you impose some serious symmetry on the initial data. Then one would have stability of this type of singularities, or if you look, for instance, in a very high dimension, not in 3+1. Okay, so these are important recent work of Alexakis, von Davlos, and von Davlos running at spec. There are lots of mathematical works, I should say, predating this, for instance, in symmetry, etc., with many contributors thinking about these type of, let's say, Schwarzschild-like singularities. So this is one part of the story about singularities, which is to say that there are a lot of singularities which are like Schwarzschild. However, they are still very non-generic. So you may expect, if you just look at this story, that there are not that much singularities after all. But there's another part of the story which seems to suggest the contrary. So this is the famous theorem of Penrose in 1965, which recently also won him a Nobel Prize. Let me state the particular consequence of Penrose's theorem. What it says is, if you look at small perturbation of Schwarzschild data and you look at the maximal Cauchy development, well, then it is geodesically incomplete, just like Schwarzschild, right? Unlike Minkowski. So what's going on here? Well, if you look at this theorem, well, first of all, the proof actually doesn't use the PDE so much. It uses a rather soft global differential geometric argument. And at the heart of the argument are objects known as trap surfaces. Well, these are surfaces which you can find plenty of in Schwarzschild, and you can easily say that they are stable. So if you perturb the data, you look at the solution, it will still have trap surface. Well, the key insight of Penrose is to say that, well, these trap surfaces are very important in, let's say, singularity formation. In particular, if you have a trap surface and under suitable global assumptions, then the solution must be geodesically incomplete. Okay, so this is how the proof goes. It goes by saying that you have these trap surfaces. But the proof actually doesn't say much more about geodesic incompleteness. Recall that in Schwarzschild, right, we have geodesic incompleteness, of course, but there's much more. You can say things are singular, things are blowing up. This proof doesn't tell you anything of that sort. Okay, so at least up to this point, things still seems consistent, although we still have to understand it a little bit more. So what it says is that, okay, if you look at Schwarzschild, maybe that type of singularity is very non-generic. However, there might be some singularities that's different from Schwarzschild, right, which arise if you perturb Schwarzschild. So the question arises, what does the generic geodesically incomplete spacetime look like? Well, for that, one actually can already see something quite interesting in what's known as the Kerr spacetime, which I'm going to go to next. But before that, perhaps it's helpful to think about a completely silly example. So here's the silly example. So recall that I told you that we have Minkowski, and Minkowski you can think of as the maximal Cauchy development of trivial data like that, right? But of course, nothing in the fundamental theorem is stopping me from considering just a subset and look at that initial data, right? So let's look at the ball. So if you believe me that the Einstein's equations are wave equations, you should think there should be finite speed of propagation. So if you have this subset, then the maximal Cauchy development would also be a strict subset of Minkowski. In fact, it's this subset, okay, like a diamond shape. Okay. So this is obviously geodesically incomplete, right? Because look at this geodesic, it stopped, okay? And you can extend smoothly. In particular, you can extend it by Minkowski. But this is rather silly because all this is due to the fact that the data is incomplete. Okay. So I don't want to think about this at all. I want to think about only complete data. In fact, I only want to consider as complete asymptotically flat data, well, like Minkowski, of course, that's flat, or like Schwarzschild. Okay, so that is to say, outside convex set, everything is close to flat. In fact, approaches flat as you go further and further away. And there's a physical reason to think about this, right? These data correspond to isolated self-gravitating bodies. So now I can tell you the Kerr example that I was talking about. So recall that I've showed you the Schwarzschild family of solutions, which is parameterized by M, which is a non-negative, a positive number. Now I want to think about a larger family for which a Schwarzschild is a subfamily. Okay. So now I have two parameters M and A. Right? A has to be less than M in absolute value. If A is equal to M, this reduces to the Schwarzschild case. Now, in general, I would have the manifold R2 cross S2 now no longer strictly symmetric, and the metric can be written down explicitly like this. As you can see, this is quite a bit more complicated than Schwarzschild, and it was discovered much later. Okay. So let's look at what's going on here. So this satisfies the condition that it's asymptotically flat. In fact, there are two flat ends like Schwarzschild data. When A equals 0, as I said, this is just Schwarzschild. And well, if you just think, if Schwarzschild, I said the incompleteness is stable. So in particular, if you look at small a, right, the development should still be incomplete. And in fact, for all a, the development is always incomplete. However, if a is not exactly 0, then there's no singularity whatsoever. Okay, so this is a bit like the silly example we had, right, where there's no singularity. You just have a finite boundary, everything is smooth. But it's just that things beyond it, whatever they are, would not be determined by data. Okay? So this boundary is known as the Cauchy horizon. In particular, this shows that even if you start with complete asymptotically flat data, incompleteness can occur without singularities. So here's the picture. So the Kerr data is this. 2 asymptotically flat n, right, with future null infinity, for which if you are in the black hole, you cannot send signals to. Okay, this is the maximal Cauchy development of the data. Okay, and at here you have the boundary, which is called the Cauchy horizon. Everything remains smooth. You can extend beyond it. There's no issue at all. Even though whatever you do here is not determined by data. But now you see that there's actually a problem, right? The problem is as follows. So you can try to extend it, and why don't I extend it with the following procedure? Let's imagine I have a hypersurface here. Let me impose some additional data here, right? I use again the Schoenberger's theorems. It tells me that I can solve the Einstein's equations here. Okay. So I have an extension which is still a solution to the Einstein's equation. However, of course, I have a lot of freedom of putting this extra data. So therefore, this extension is highly non-unique. So I have highly non-unique extensions, still as solutions to the Einstein's random equation, but it's independent of the data here. Okay. So this creates a non-uniqueness problem. So now, even though for an observer, right, of course, they would maybe prefer the Kerr case because, well, they are not infinitely torn apart. They still are in the smooth space-time. However, from the point of view of a closure of the theory, this is the problem because there are infinitely many smooth solutions which still solve the PDE. Okay, so it turns out that one might expect that Kerr, when A is non-zero, is a non-generic case, so that everything is okay. Okay, and this is the content of the strong cosmic censorship conjecture of Penrose in 1973. And in modern language, is the following. It says that if you look at the maximal future Cauchy development to, importantly, generic asymptotically flat initial data, they should be future inextendable as suitably regular Lorentzian manifold. Okay, so for generic data, you don't see something like Kerr with A not equal to 0. You see something like, well, either Minkowski, where everything is global, or if you're not global, you're incomplete, you will see something more like Schwarzschild. Well, if you think this is the case, right, and we'll hope this is the case, you have an immediate issue, you would think, is that, well, Kerr is stable. Okay? So this is something that in the mathematics community, one has worked on for a long time, and finally, very recently, we have the final statement by Georgi, Kleineman, Shaftal in a series of paper involving different combinations of the authors. And what the theorem says is that if you look at initial data, right, which is close to Kerr, perturb Kerr a little bit, but with A very, very small, okay, then you look at the maximal future Cauchy development, it would have at least a region, which is I'll call the exterior region, the outside of the black hole, which is stable, stays close to Kerr. In fact, it will converge to some possibly different Kerr, right, with different parameter. Yeah. So in the special case where A equals 0, where it's Schwarzschild, there's a similar theorem by Defremers-Hosego, Rodniansky, Taylor, slightly earlier, when you suitably mod out the A non equal 0 solutions. So generically, you can moreover say that I have that Kerr is with small angular momentum, small a, are stable. It's easy to see from this theorem that generically the final parameter a would be non-zero. Okay, so you may think that this might be a problem to strong cosmic censorship conjecture. Well, because precisely that the problem was with these not equal 0 A's. One should of course also say that many people contributed to this this final form of the theorem. One may hear more about this later in the Congress in the talk of Hinz and Holzhegel. So here's a picture. If you look at data, perturbed close to Kerr, everything in what I call the exterior region outside the black hole would be stable. In fact, you converge to some other Kerr. Okay. Now, fortunately, even though the final parameters A might be non-zero, the stability theorem doesn't tell you anything about the inside. So it's still consistent with saying that, well, if you perturb, you might have a singularity inside. Okay. So Penrose actually has an argument why this should be the case. So, well, what he said is that the Cauchy horizon generates a blue shift instability. So even though the exterior region is stable, this blue shift is going to overcome it and create a singularity. And this has been studied quite extensively in physics. And what one expects is that this blue shift will create a singularity that's very strong, like Schwarzschild, because Einstein's equations are highly nonlinear. So there are a couple of ways to say this. One is to say that, well, if I look at generic data, they should be inextendable in C0. Okay, so that would be like Schwarzschild. That would be related to saying that tidal deformation are infinite. Another point of view that's often said with respect to the genericity of Schwarzschild is to say that, well, if you look at generic asymptotically fed data, you look at the maximal Cauchy development, the finite future boundary should be space-like, just like the Schwarzschild case. Okay. So let's try to investigate whether this is true, whether one can prove these conjectures. To summarize, we know that Schwarzschild is a singularity, it's geodesically complete, and there's a space-like singularity which is much more severe. Geodesic incompleteness itself is stable. If you perturb a little bit, then you still have geodesic incompleteness. In particular, Kerr is geodesically incomplete. However, it has no singularities. But one expects, if you look at perturbation of Kerr, then you get some singularities back. That's the strong cosmic extension conjecture. And one expects it shares some features of Schwarzschild, though one should caution that maybe locally it should look different from Schwarzschild, according to the Lifshitz-Skladnikov heuristics. So what exactly is the answer? Well, it turns out that, in fact, if you look at perturbations of Kerr, the interior would be very different from Schwarzschild. So this is a theorem joined with Mihaly Staffirmus in 2017. What one can say is that if you look at initial data to the Einstein's vacuum equations, which is close to current initial data with, again, small angular momentum A, but non-zero. In fact, one can also think about large A if you also have the stability of Kerr exterior. But in any case, what one says in this theorem is that suppose you look at this data, then in fact the solution would have a bifurcate Cauchy horizon. So the diagram that you would draw would be like the Kerr diagram, not like the Schwarzschild diagram. Moreover, the metric is actually extendable in C0. And in fact, it's everywhere C0 close to Kerr. So this is the theorem in picture. Data close to Kerr. Stability of Kerr tells me that in the exterior, everything converges to Kerr. What we say that inside, you have exactly the same diagram as Kerr. In fact, you can extend further in C0. Okay. Well, at this point already, you can say that the C0 formulation of strong cosmic censorship conjecture is false, and the space-like singularity conjecture is likewise false. Now, is this the end of strong cosmic censorship? What about determinism? Well, it turns out that there's a more interesting story behind this. In order to gain further insight, let's try to look at a slightly different problem. I want to look at a strictly symmetric model problem. Of course, about Kerr is not strictly symmetric, so I can't talk about Kerr and strictly symmetry. So let's look at Reissner-Nordström, which is not a solution to Einstein's vacuum equation, but it solves the Einstein-Maxwell system. The important point is that this is still strictly symmetric, and it has the geometric features of Kerr. In particular, it has a smooth Cauchy horizon, it can be extended non-uniquely, etc. Diagram of Reissner-Nordström, the same as Kerr. So I can pose a strictly symmetric problem, which is the strictly symmetric Einstein-Maxwell scalar field system, well, the important thing to think about is that this is a strictly symmetric model problem for Kerr. Okay. So what can one say? It turns out that with spherical symmetry, the analog of stability of Kerr exterior and stability of Kerr Cauchy horizon was known more than a decade earlier in the work of Wronnianski. So if you look at strictly symmetric data to the Einstein-Maxwell scalar field system, assume initially that Maxwell field is non-trivial, thought of as a genericity condition. Then, well, the first thing is the analog of stability of Kerr, right? Reissner-Nordström is stable. The exterior region converges to Reissner-Nordström. Now, the second thing is that if you look at small data, if you look at data which is a small perturbation of Reissner-Nordström, then the maximal future Cauchy development would again have a diagram that looks like Reissner-Nordström. In particular, everything is C0 extendable. So this is again the diagram. However, in the case in spherical symmetry, one can say more, and one can say that finally something is still singular. Okay. So this is a joint work with Songjin Oh, again in 2017. What we say is that, okay, if you look at all data, well, there will be data that give rise to Reissner-Nordström. But if you look at generic data, we can find an open and dense set of data, right? Such that if you look at the solution, right, it would be C0 extendable. However, it's not C2 extendable. So at least some sort of curvature blow up is there. In fact, the Cauchy horizon generically would be a global weak null singularity. Right? So the singularity is null. It's weak because it's still C0 extendable, but it's singular nonetheless. So in particular, there would be no extension so that you solve the Einstein's equation classically. One might even hope, so that's not known yet, that there are no extensions as weak solutions. So back to vacuum, back to Kerr. Do we expect a similar picture in vacuum? Perhaps the first question to ask is, do we expect these weak null singularities to be stable without symmetry, to be stable in vacuum? The answer is yes. Weak null singularities are stable, so one can construct them, one can show that they are stable, much better behaved than the singularities are constructed with von der Waals. So because of this and the insights we gain in spherical symmetry, one may conjecture that for generic perturbations of Kerr, the black hole interior, in fact, has a weak null singularity. In fact, a lot of progress has already been made for this conjecture. It seems that for now, the main remaining ingredient is to understand in the exterior the rate of convergence. Okay, and there are lots of ongoing work of different people trying to understand this. Now, finally, I want to end the talk by thinking about not just the stability of the black holes that we know, but I want to think in the context of gravitational collapse. So what do I mean? So in astrophysical black holes, in fact, the black holes does not look like quite the black hole that we have been considering before. Well, for one thing, the black hole we have been considering before have data which are on R cross S2. Physical black hole comes from collapse of data from R3. And moreover, black holes we have been considering before, well, let's say Schwarzschild, either already they have a trap surface, right? Remember, this is an important object identified by Penrose in the formation of singularity, or they have a trap surface towards the past. So I want to consider a scenario where really I don't already put trap surfaces in the data. I want to say that the trap surfaces form in evolution and eventually collapse into a black hole. In a very remarkable work of Christodoulou, about 15 years ago, he showed that this is actually possible. You can actually find initial data. You have gravitational waves focusing, right? So all going in. And if it's sufficiently strong, that eventually you will form trap surfaces here. Okay. So now I want to understand space-times arising from this. Well, first of all, one can say that this, at least a subclass, would actually form a black hole. So look again at this picture. So let me draw this data. Right. So now this is one-ended. I only have all three data. I have focusing of gravitational waves. Eventually, I form a trap surface. Let's say here. Okay. I can cook on my data so that things are like Kerr here. Let's say. So then, by stability of Kerr, I know everything would converge to Kerr as you go here. suitably localizing my theorem with the Fermis, we know that, well, in fact, you have a weak null, well, you have Caesar extendability here. You might expect that it's also a weak null singularity by what we said before. But now, well, there's no two and, right? I wouldn't have something that connects to the other and. Now I want to understand what's going on here. For instance, are things going to just close up, or what's going to happen here? Would there be some other singularities? Again, things we don't know, we would look first in spherically symmetry. In the recent work of Van der Mortel, he showed that in a spherically symmetric model, in fact, if you have a weak null singularity, it cannot close up and it must break down. Very speculatively, one may conjecture that maybe this is also the case for generic vacuum spacetime. You look at data on R3 approaching Kerr in the exterior, maybe the interior would have a weak null singularity, which eventually break down. If so, this will be, again, an example of some space-like singularity. So let me finish the talk here. Thank you very much for your attention.
Thank you. Thank you very much, Jonathan, for this very nice and instructive talk. And I also want to thank everybody for watching us, and hope you will be able to join the rest of the meeting as well. Thank you so much, and goodbye now.